All right, so here are your notes for 4.6. Be able to identify imaginary numbers, be able to perform operations with complex numbers, and be able to solve quadratics involving complex numbers. Um, so there's the three goals. We went over a lot of this in class. I'm going to skip through the first couple parts here. Basically, these two I had you solve in class, and you found out this one ended up with a square root of a negative, which in Algebra 1 you were told did not exist. If you had a teacher that told you that, they weren't being very precise because square root of -1 or negative numbers do exist. Um, it's just you didn't learn about them in Algebra 1. You're learning about them in Algebra 2. A little bit of history here. Square root of 25. So I'm going to go fast over this. So we went in a lot more detail in class. But basically, this guy came up with the idea that you could actually take a square root of a negative. This guy made up the rules of how you do that. So how you would take square roots of negatives and do operations with them. So this guy did that. This guy had the idea. This guy made up a bunch of rules on how to work with them. This guy called them, he didn't really call them crazy, but he said that, hey, you guys doing all the work over here, that's all imaginary stuff. Why would you take the square root of a negative? It does not exist. So these guys were just kind of saying, hey, what if it did exist? We could do all this math. This guy said, why are you even doing that? It's all imaginary. So he actually made up the word imaginary. That's why we call them imaginary numbers. But it turns out it's not imaginary. They actually are real numbers that these two came up with. The only thing is that they were it wasn't applicable to the stuff that they were doing at this time. Like back in 1572, basically they only needed math to build bridges, make roads, make buildings, things like that, which you would never end up with a square root of a negative when you're working with those type of equations. Turns out the types of equations that end up with square root of negatives come up when you start trying to do math with electrical things dealing with electricity. Computer science, electrical engineering, that type of thing, those things actually end up with equations where you take square roots of negatives. So these two they basically started thinking about stuff that had no application or actually didn't exist at the time. Um, I'm actually using that word didn't exist isn't really right, but basically they did stuff that wasn't used. So people like this Descartes guy said, hey, that's imaginary stuff, but then he was proved wrong because today we actually use it so that we can make cell phones and computers and all that nice, neat stuff that you like to use on your free time. Um, so yay, go Raphael and Heron. Okay, so that's the history behind it. Now the thing is here, main reason why I wanted to go over this is because even though it's called imaginary, it was because it shouldn't be called that anymore. They should have changed the name once they figured out that it actually is real. These imaginary numbers are actually real numbers that can be used. They should have changed this to like some other word. My vote was for like an Aguirre number, but yeah, no one listens to me. So yeah, that's the theory behind that. So even though we call it an imaginary number, it's not like it doesn't exist. They actually do exist. It's just this name never changed. Okay. Um, Look, there's already an A and a G and an I. So it's almost a Geary already. Anyhow, so imaginary unit definition. So what happened here was that they defined the letter I as being the square root of -1. Um, so the reason why that helps out is this. Let's say you had the square root of a -25. You can always break a negative number into a -1 times a positive number. So in that case, you have square root of -1 times the square root of 25 using the product property. And then now this is the only piece that's really causing a problem because you can actually evaluate square root of 25 and get a 5. So what they said was instead of having to write this over and over and over again, we're going to go ahead and call square root of -1 I. So turns out the square root of negative 25 is 5I. So that's the way that works. So basically, whenever you have a square root of a negative, just break it apart like that and bring an I out. Now another thing is here, all I did here was I squared both sides. This becomes very useful because sometimes you'll end up with an I squared. So if you square this side and square this side, I squared is just I squared. If you square root of -1, remember squaring and square roots are inverse operations, you can just get left with a -1. So not only do we have I equals the square root of -1, but if you do a little bit of work, you get I squared equals -1. Reason why I bring that up is because if you see an I squared, you should just replace it with a -1. Standard form complex number. This is called a complex number because it has two parts. The first part is considered the real part, and second part is considered the imaginary. So that's because of this I part right here. So that's why it's considered complex, because there's a two part. And yeah, so let's move on because, like I said, we've been over this in class. All right. Okay, so simplify the see what happens when I go fast? I can't talk. So like I said, you should break off a -1 there times 20. This is square root of -1 times square root of 20. Square root of -1 is an I. And now this part you can just evaluate the same way that we've been doing. So 20 is a 4 times a 5. 4 has a perfect square, so that's going to be a 2 square root of 5. Now, since these are multiplication, you can flip them around all you want. In most books, it's written like this: 2 times I square root of 5. Then bring the I there. Some books, I have seen it written like this also: 2 square root of 5 I. But most of the time, it's like this. Okay? So that's basically how you guys simplify square root of -20. Operations. So now that we can identify, so we just identified what this letter I is. I is the square root of -1. Let's go ahead and do some operations. So operations, adding, subtracting, multiplying, and dividing. Now this is using the letter I. The nice thing about this is that the letter I works a lot like a regular variable, meaning when you have like terms, like if you had a 5x and a 7x, you would add those together and get a 12x. So just like that, with a 5i and a 3i, you'd add those together and get a 8i. So you already know all the rules for working with complex numbers, as long as you know how the rules work with variables. Now, one major difference is if you see an I squared. It should be replaced with a -1, and that's because of the definition of what I is. It just feels weird when I say that. Definition of what I is. Sounds like bad grammar to me. That was defined over here, so that's what we did there. Since an imaginary unit is a type of square root, it also should not be on the bottom of a fraction. We went over this before too. That whole bottom of a fraction thing doesn't really apply nowadays. Having a square on the bottom is actually acceptable. It's before it just became, the math was a lot harder before they had computers. So with the square root on the bottom, so they ended up rationalizing the denominator. It's still a valid technique though, because it helps with your math skills. But yeah, I personally don't think it should be a rule anymore to not have on the bottom. But anyways, so let's go ahead and do these four. Write each of the following as a complex number in standard form. So remember, that's a plus bi. So first off, just imagine like these i's were x's. If you had a binomial plus another binomial, you could actually distribute. There's a 1 here you can distribute and actually get those apart. Now, very careful. This is a plus sign. It's not multiplication. It's not like this one where you would actually distribute twice. This one is actually just a plus sign. So what you're going to do is first you're going to drop your parentheses. Because there's a 1 in front, you can distribute there and distribute there. So you're going to get a 4 minus I plus 3 plus 2i. Now it's just a matter of combining like terms. So I'm going to go ahead and combine my 4 and my 3. That makes a 7. And I'm going to combine my negative I and my positive 2i, which makes a plus I. Okay. And remember, this should be an a plus bi form. So your a is your 7, and your b is technically a 1, but you don't got to write it. So a plus bi, and your b is a 1, but it's not there really. All right, and that's it. So simple as that. And remember, I is the square root of -1, so technically that's what this is. It's just a shorter way of writing it. Think of this like a nickname for square root of -1. Hey, I, yeah. Okay, never mind. So now we're going to distribute. Like I said before, it works just like a variable. So if that said 5x times -2, you'd put -10x. But it's an I, so you're going to put in -10i. 5i times I would be like a 5x times x would be a 5x squared, but it's not an x, it's an I. So plus 5i squared. Now, one thing here, I see an I squared. I squared can be replaced with a negative 1. So what happens here is you get negative 10I, and then 5 times negative 1 is a negative 5. So that actually turns into minus 5. Now, this is not right because it says complex number in standard form. We have our imaginary part before our real part, so we got to flip that around. So that's negative 5 minus 10I. Okay, how much time we got here? Oh, I gotta hurry up. Okay, so this one, whoa, I did A then C. I didn't even notice. I would skip B. So here's your B part. Similar to the addition one, you have a 1 in front, 1 in front. You should distribute, so it's 7 minus 5I. Keep in mind this is a negative 1 times a 1, which is a negative 1. Negative 1 times a negative 5I, which is a plus 5I. Now what you're going to do is actually combine these two together. Those are opposites, so actually they're gone. Because if you had a 5x and a negative 5x, they would cancel out. 7 minus 1 is a 6. It says a complex number in standard form. I think I told you guys I wanted to throw the zeros in, but that's fine. You can leave it like this. A plus bi. Basically, all you have here is a real part. You don't have an imaginary part. So that's a real number. Your bi would be a 0i, but you don't have to write it. Okay, next part, you're going to multiply these. So keep in mind this is like a double distribution. You got a binomial here being distributed. So first distribute your 7. So 7 times a negative 1 is a negative 7. 7 times a 2i is a plus 14i. Okay, so that's done being distributed. Now you're going to distribute the second term, which is here. So negative 4 times a negative 1 is a positive 4i. Negative 4 times a positive 2 is a negative 8i. Squared. Oops, I forgot my squared there. So there you go. Now let's keep simplifying. These two come together, combine like terms. So you get a negative 7. That's an 18i. Now this I squared part, remember, is a negative 1. So technically that says negative 8 times negative 1, which is a positive 8. Hopefully you're kind of catching on now that when you have an I squared, it's basically what's happening is it's switching the sign of whatever numbers it's attached to. And one more combination here. I'm going to go and put my real numbers in the front because it should be a plus bi, so that's going to be a 1 plus 18i. So in this case, my a is a 1, my b is an 18, a plus bi. And that's how you perform operations. So if you notice, we did addition. This was one complex number plus another complex number. This was subtraction. This is a complex number minus a complex number. This is my multiplication. This was actually another type of multiplication, but it was, I guess some people call it the foiling method, but it's actually distribution, double distribution. There's one operation that we're missing, and it's division. Now, before I teach you the division, I do need to show you something. Basically, there is a method to turn any complex number into just a real number. That way is called multiplying it by what's called the complex conjugate. So basically what you do is you take the complex number and then you multiply it by 4i. You change the imaginary part of the complex number's sign. Not both signs, just the imaginary part. You switch the sign. So if this was a 3 minus 5i, you'd do 3 plus 5i. The real part number does not change. So the reason why this works out is because when you multiply these, 3 times 3 is a 9. Okay? So I'm going to distribute twice. 3 times 3 is a 9. 3 times negative 4 is a negative 12i. And then when we distribute the second part, 4i times 3 is a positive 12i. And then 4 times negative 4, that is a negative 16i squared. Since we chose this for this, that's the whole reason why we chose this, because when you switch the second sign right here of the negative of the I part, what happens is it actually cancels in the middle right here. The negative 12i and the positive 12i will cancel out. That's the whole reason why we picked the opposite sign. Now the I squared part doesn't really matter. So it's 9 minus 16i squared. The reason why I say it doesn't matter is because we have I squared. And if you remember, I squared can be replaced by a negative 1. So this is actually 16 times a negative 1, which is basically 9 plus 16, which is a 25. All right. So that's how you turn a complex number into a real number. So we turn that into that by multiplying by this. Now, you're not allowed to just go around and start multiplying stuff because it changes the, you can't just go up and say, hey, I want to multiply this by a 7 because it won't be the same thing anymore. Now it's 7 times that thing. So if you remember, I taught you guys about the fancy ones. So right here, we're going to write it in standard form. Oh, beep. Sorry about that. And hold on. Alrighty. Now that that bell has stopped ringing, so I forgot what I was doing. Oh yeah, so this is counting as a division. We went over the other operations, and then now we're going to divide. This is a complex number divided by another complex number. It's basically a fraction. So what we want to do here is we want to get it in simplest form. Now it actually looks like it's in simplest form because remember, simplest form means that everything's out of the radicals. Remember, technically I is a radical. It's a square root of a negative 1. Now the problem is on the bottom. You're not supposed to have a radical on the bottom. So what we're going to do here is this. We're going to use that method that I just showed you, the complex conjugate, in order to get the imaginary part off the bottom. So remember, you can't just go around multiplying by anything you want, because once you start multiplying by something that changes its value, you are doing something wrong. So like I can't just put a 2 here, because then you'll double the value of whatever this is. So the only number you can multiply by and not change values is a 1. So we're going to do a fancy one here. So we're going to pick our 1 very wisely and say, okay, I want to cancel out the imaginary parts, 1 plus 2i. We're going to use a complex conjugate of the bottom part because the bottom part's the part that we need to turn into a real number. So you're going to do 1 plus 2i on the top also. Remember, this is just a 1. Anything divided by the exact same thing is a 1, so it doesn't change the value. So now what we have is this. On the top, we have a 5 plus a 3i times a 1 plus a 2i. On the bottom, we have a 1 minus 2i times a 1 plus 2i. So what we're going to do here is, I'm going to move it over. Oh, that's so much stuff. Okay, I'm going to move all of this down over here so I have some room to work. Come on. Doesn't want to go back together. So anyways, I'll do the top in green. So just focusing on the top part, I have a double distribution here. So I'm going to distribute the 5 to the 1. 5 times 1 is 5. I'm going to distribute the 5 to the 2i, which is a 10i. Then I'm done distributing the 5. So now I'm going to distribute the 3i. Those of you that use the box method, feel free to do that too. So I'm going to distribute my 3i. 3 times 1, 3i times 1 is a positive 3i. 3i times a 2i is a 6i squared. All right, so I'm not quite done with the top, but I multiplied it. It just needs to be simplified a little bit. So I'm going to go ahead and multiply the bottom part also. This is just another double distribution. Now, those of you who kind of caught on to this pattern here with this plus and minus stuff, you could go ahead and not show this step, but I'm going to since these are your notes. 1 times 1 is a 1. 1 times a 2i is a positive 2i. Done distributing the 1 now, so now we're going to distribute the negative 2i times a 1 is a negative 2i. And negative 2i times 2i is a negative 4i squared. Now, a couple things here. We're going to distribute. We're going to simplify the top and simplify the bottom. Now, I'll do this in red. On the top and the bottom, we have an I squared. And if you recall, I squared is a negative 1. So those will change signs. And then also we're going to combine like terms here. And on the bottom also. So that's what we're going to be doing to simplify this thing. I don't want to go down that way, so I'm going to move all of this stuff. Hold on 1 second. one large group. And let's move it over some. All right, so now what we're going to do is just simplify this. So the 5 stays the same on the top. This part, when you put it together, 10i plus 3i is a 13i. And this part right here, that's a 6 times a negative 1, which is a negative 6. So there is still a little bit of work to be done there, but let's go ahead and go to the bottom though. Positive 2i and negative 2i, those are gone. That makes a 0. So we'll have just a 1, and then we have the negative 4 times the negative 1, which is a positive 4. All right, so now it's just a matter of combining like terms. 5 and a negative 6 is a negative 1 plus a 13i, and then on the bottom is a 5. Now keep in mind, we want this to be an a plus bi form. Right now, it's not really separated like that, so what we're going to do is we'll divide the 5 into the negative 1, so you get a negative 1/5, plus 13i divided by 5 is the same thing as a 13 over 5i. That way you can identify what your a and your b are. Your a is a negative 1/5, your b is a 13 over 5. All right, how much time? Wow, okay. These are going to be long notes, by the way. Graphing complex numbers. So now that we know how to work with them, operational wise, I do want to show you guys how to graph them also. Now, this ties into number lines. If you wanted to graph a 3 on a number line, basically what you would do is you'd start at 0 and then go 1, 2, 3. There's your 3, and you plot it. Same thing with imaginary number lines. It's just now you have this unit of I on there. So what you do is you go 0i. That means you have no i's. This has 1i. This has 2 i's. This is 3 i's, and so on and so forth. So if you have a 3i, you're basically going to go over 1, 2, 3, and then plot your point there. That's how you graph on an imaginary number line. So graphing real numbers on a number line, graphing an imaginary number on a number line. By the way, I was just counting there. You don't have to put those. Now, remember, a complex number has a real part and an imaginary part. So we got to put these two number lines together. So basically what's going to happen here is this, if I can get this done right. Just like with the x and the y, let's see here, I'm going to group it and rotate. So in order to put two number lines together, there you go. You now have what looks like a coordinate plane. You basically just overlay one number line on top of the other number line to graph a complex number. Because there's two parts, you need two number lines. So that's what you would do with those. So plot the following. This is called the complex plane. So what used to be your x-axis, this is now your real axis. So this is going to be your real number line. What used to be your y-axis, this is now your imaginary axis. And that's what's called the complex plane. So it's no longer x and y, it's real and imaginary. So this first one, so what you want to look at here is a plus bi. You want to figure out what your a and your b are, because your b is your imaginary units, a is your real units. So right here, a is a 2, and then b is a negative 3. So think of it kind of like a point. It's almost like your real part is your x part, and your imaginary part is your y part. So on your x part, or your real part, you're going 2. So the real part, you're going to go to the right 2. 1, 2. Now, it has two movements because now you want to go to negative 3 on your imaginary number line. This is your real number line. This is your imaginary number line. So negative 3 on your imaginary number line goes down 3. 1, 2, 3. So your point is right here. That is the point of 2, negative 3i. Now let's try this one. So this one, your real number is negative 3. So you're going to go to the left 1, 2, 3 on your real. Your imaginary part is a positive 2. So you're going to go up 2 on your imaginary line. And there's that point. Okay. And last point, 4i. So remember, this should be a plus bi. So since there is no real part, your a is a 0. So you're starting right at your origin, and then you only have an imaginary part. So that's the part that you're going to move. So you're going to move 4i. So this is 1i, this is 2i, 3i, 4i. So That's where that one is. Okay, so we just graphed 3 separate points. That's how you would plot a point complex number, is that you would need the 2 number lines, and that's it. So if I ask you guys to plot a point, that's what you're doing. All right. Ooh, long time. All right, so absolute value of a complex number. Now, if you remember the meaning of absolute value means that you're finding the distance from 0. So once you find the distance from 0 of a complex number, you think about it, a complex number can only be graphed on here. So the distance from 0 is from the origin. So that's what we're actually finding when we're finding the distance. So if you want to find the absolute value of a complex number which has 2 parts like this, you're actually going to use this formula right here, square root of a squared plus b squared. The reasoning behind that is this. Let's say you had an imaginary number right here. Okay? So we'll say we plotted it, it was right there. Now, we don't know how far we went. Well, here, draw this. So we don't know how far we went this way, right? Because I didn't write any numbers. So that's the real part. We'll just call that A. A can be any number. Say it was like 10. We moved over 10 spaces. Now, we don't know how far up and down we went either. Okay? Because up and down movement is your imaginary part, so let's call that B. B can be a 17. I don't really care. Now, the thing is that we got to find the distance from this point to 0, which is over here. So we're actually trying to find this green side right here. So that's what it's actually asking for when you're finding absolute values. Now, if I take away this coordinate plane, that's an actual triangle. Hopefully from geometry, you remember this, because a squared plus b squared is actually equal to c squared. The thing is that I don't want c squared. This is just a c. So what I'm going to do is I'm going to take the square root of both sides. So c is actually equal to plus or minus the square root of a squared plus b squared. But since we are talking about a length, we don't need this negative part. So we just want c equals a squared plus b squared. We got the squared. That's where that formula comes from. This right here, a squared plus b squared. So if you want to find the distance from a complex number, which is a point, to 0, that's where this formula comes up. All right. And I think this is the last example. We got more. Okay. All right. So perform the given operation and find the absolute value of the complex number. So perform the operation. The operation is multiplication, so we're going to multiply here. 7 times a negative 1 is a negative 7. 7 times a 2i, so we're distributing this 7, is a 14i. This part is going to be a positive 4i, and this part is going to be a negative 8i. These two combine. This I turns into a negative 1. So it's going to be negative 7 plus 18i. And that'll come up plus 8. So this is going to be a 1 plus 18i. Now that we just performed the operation and got that complex number. Now there's actually a second part that says find the absolute value of it. So now what we're going to do is use the formula square root of a squared plus b squared. So our a part is a 1, our b part is an 18. So we're just going to plug it right into the formula here. It's the square root of 1 squared plus 18 squared, which is square root of 1 plus, let's see here, 18 squared, 324. Okay, and this will be square root of 325. Okay, and let's see, is there any perfect squares in there? 25. So square root of 25 times, wait a minute, yeah, 25 by 13, is that right? 18, 324, 25 times 13. Okay, and so this is going to be 5 root 13. So this was a two-part answer. First it said perform the operation, so we performed the operation, and then it said find the absolute value of that complex number, which is this one. So this is simplified. This is if we were to find the distance of this number from 0. All right. Solving quadratics is finding x-intercepts of parabola. We went over this many times before. To find an x-intercept, you put a 0 here, equals 2x squared minus 8x plus a 3. And then you can solve this by factoring, things like that. But basically what I'm trying to get at here is that when you solve an equation, a quadratic equation, you're finding an x-intercept. So you're actually finding the x-intercepts of the parabola. Now this tells you a lot. So what does the graph say? It says that basically, if your graph is like this, you have two x-intercepts, which means you have two answers when you're solving, because when you solve, you're actually finding x-intercepts. So say you knew the equation of this parabola. When you solved it, you know you'll have two answers. Now, a parabola that sits on the graph like this would only have one answer because there's only one x-intercept. Now, a parabola that's off of the graph has no x-intercepts. Now, keep in mind, what that actually means in our case is that it has imaginary numbers for its intercepts because you cannot graph imaginary numbers on an xy plane. It has to be a complex plane, a coordinate plane. So that's basically what it's saying, is that if you have imaginary answers, that means your parabola is not touching the x-axis. If you only have one answer when you're solving, that means that your graph would have one intercept. And if you have two answers, that means that it's like that. Okay. Last example. So now that we've worked a whole bunch with square roots, this is of negatives. This is what it's going to look like when you actually do it out while you're solving. So this one right here, if I told you to solve it, you do minus 10. Okay, so you get a 3x squared equals negative 36. And then you divide both sides by a 3. So x squared equals 12, negative. All right, so at this point, you're going to take a square root, and you should be noticing that you're going to get imaginary numbers. So right away, you would know that if you were to graph this thing, your graph would not touch the x-axis, okay? So that's what this is telling me right now, so I'm going to have imaginary answers. So x equals plus or minus the square root of a negative 12. Keep in mind, negative 12 can be broken up into a negative 1 times a 12. So at that point, you would take the I out, plus or minus I square root of 12. And there's a 4 inside of there. That's a 4 times a 3, so you can take out a 2, plus or minus 2I square root of 3. And I did want you guys to split that. This equals 2I square root of 3, or x equals negative 2I square root of 3. So these are your x-intercepts, but they don't exist on the x-axis because they are imaginary parts. All right, so that's what that actually means. And that's how you guys use it within the solving. So you're solving the exact same way, it's just you're pulling the I out of that using square root of negative 1. Homework worksheet 4.6, have at it. So it took about 33 minutes. Wow, that's a long video. So good luck. Tomorrow we'll actually go over some of the homework problems that you guys have if you have any. Okay, bye-bye.